So what is test case reduction? If you're John Hughes, test case reduction is shrinking. If you're everyone else, it's test case reduction. There was basically, like, it was invented in two different places as early on, and we've sort of split on the naming, but they're exactly the same thing. So if you were in John's talk earlier, all the things he was saying about shrinking, that's what I'm going to be talking to you today, but in a slightly different context. And that context is this. From the other big work, I'm going to be talking about a different John Regier's work for a lot of this, which is in the context of C programs. So suppose I'm writing C, I compile my program, I run it, and this happens, segfault. So far, this isn't very surprising, right? Like, this is the normal experience of writing C. C is practically a DSL for writing segfaults. But we want to figure out what's going on, so we compile it again at a lower optimization level, and we run it, and this time it doesn't segfault. It just sits there running. And that might be fine. Maybe it's meant to do that. In this case, it is meant to do that. This program is not a very useful one. It's just an infinite loop, but it's an infinite loop that sometimes segfaults and sometimes actually runs as an infinite loop. So what's going on? Obviously, it's not a compiler bug. Compiler bugs don't happen, right? Compiler bugs happen. They don't usually happen when you're writing C. But a lot of us aren't writing C. A lot of us are writing in other languages. Many of them are more cutting edge. This is an alternative conference, so we're using a lot of cutting edge technology, which means it doesn't work yet. When I was writing Scala about a decade ago, I was hitting a compiler bug on like a weekly basis. I don't write Scala these days, so this allows me to pretend that it's gotten better. But in this case, it really is a compiler bug. The other reason why it's usually not a compiler bug in C is that it's so hard to write correct C and so hard to avoid undefined behavior that you've probably just done something that means that the compiler is allowed to do whatever it wants. In this case, it is a compiler bug, I promise. It's a compiler bug in an old version of Clang. Modern versions of Clang are much harder to break this way, but this one I happen to know is a program that is genuinely free of undefined behavior because it comes from a program generator that is designed to find bugs in compilers. Which means that we should probably report this bug to someone, right? The compiler is broken. That's kind of important. Someone needs to know about that. The problem is that our code looks like this. And this is just a tiny segment of it. The actual thing, I think, in this one is like about 16 kilobytes of code. It might be larger than that. If we report that to the to the Clang developers, they're not going to have nice things to say about us, right? This is particularly a problem when your bugs come from real code, because there it's not just that your code is large, it's probably also proprietary. It's the Clang developers won't like you for submitting it, and neither will your boss. And certainly your boss won't want you to admit that your code looks like this to anyone in the public world. And what we would like to do is we'd like to submit something that looks like this. This is a nice, small, it's technically not undefined behavior free, because there is one piece of undefined behavior that none of the compilers take advantage of and no one remembers, which is that infinite loop with no side effects is actually undefined behavior. I think. I may have that wrong. I'm not a very good C language lawyer. But either way, like this is close enough to undefined behavior free that if we were to give this to the Clang developers and say, hey, this segfault set 03, they would pay attention and they would go, oh yeah, that's weird. That's not supposed to happen. And so this is essentially the big thing about test case reduction, is that when we report bugs to someone, we want to use small examples. And not just small examples, we want to make them readable in general. And this is particularly important if you work in property-based testing or other forms of fuzzing or anything like that, because there is no you. There is just a program, and you need to tell the program how to produce good examples that won't make your users hate you. And so you do need to automate this process of test case reduction and producing small examples. So like, how do we get there? What do we do? Automated test case reduction, basically it has three components. You need your initial test case, the thing that actually triggers the bug. Test case reduction is not about generation. That's someone else's problem. We're not going to be talking about that much today. You need an interestingness test, which is some way of taking any test case and saying, do I care about this test case? Is this test case is interesting? And you need a test case reducer, which is what we're going to be talking about and most of what I work on right now. So So the test case is usually the thing that triggers a bug. It might be something else. You can use anything you like as a test case, as long as it satisfies some interesting property. As I say, for my purpose, these are usually generated things, but for your use cases, unless you're actually working in test case generation, you'll probably use this on things you've encountered in the wild from real data. An interestingness test can be anything at all. There's some interesting work, no pun intended, of using these with coverage targets and things like that. But for the most part, this is that the test case triggers some bug of interest. So in our earlier example, the fact that there was a seg fault when we compiled the thing, that is what makes it interesting. And the test is some way of telling a computer how to distinguish the interesting test cases from the non-interesting test cases. These are harder to write than you think, and I will talk about that quite a bit more shortly. And you need a test case reducer, the actual thing that automates the work for you. We are mostly going to be seeing C-reduce, which, as I say, is due to John Regier and a whole bunch of other people, and is specialized for this problem of dealing with C programs specifically. It works on anything, but essentially it works directly in proportion to how much it looks like C. It will look fine with JavaScript. It will work fine with JavaScript, Rust, Scala, anything that's a mostly bracey language. It might not work. It doesn't work so great with Python. It works sort of okay, and various other things it works differently well. I have a test case reducer, of course, because this is my work, called shrinkray. Shrinkray is much, much newer and less mature than C-reduce. I think it's pretty good, but for C programs and the like, you should definitely be using C-reduce and not shrinkray. But the goal of shrinkray is to basically widen the field of what's possible and to work increasingly well on things that aren't C program-like. Right now, we'll see a little bit about this. I'm not going to talk too much about shrinkray, but yeah. And if you're using property-based testing libraries, you're definitely using test case reduction. It's just, as I said, it's called shrinking there. They are essentially the same thing, though. And you can write your own test case reducers. Test case reducers are not hard to write. Writing a test case reducer at the level of C-reduce or shrinkray, that's hard to write. But if you have a specialized problem that needs test case reduction, you can write a test case reducer in like a couple hundred lines of code. It's very easy. We'll see one later. So we've got a test case. We've got a test case reducer. That will be C-reduce. What we need is an interestingness test. This is an interestingness test. I usually write them in Python because I hate writing shell. You can write them in anything you want. And this is just automating what we did beforehand. You have a source file, which is called myprogram.c. We run it, we compile it at O3 with Clang. If the code doesn't compile, that's not interesting. An interestingness test with C-reduce exits 0 when the file is interesting and non-zero otherwise. And so here what we do is we compile it, we run it. If it exits with a signal, in Python that's return code less than 0, then we say it's interesting, otherwise we say it's not interesting. If anything times out, we say it's uninteresting. And this isn't particularly good code. Interestingness tests almost never are, because they're basically just one-off scripts that you're writing for a specific purpose. And so yeah, now we have a complete set. Now we can do test case reduction. So we run C-reduce, we pass it our interestingness test, we pass it our test case, and we see something like this. We'll see it gradually cutting down the size of the program, trying these different passes that make different transformations to it, and after a while running, we will end up with something that looks like this. You may or may not see the problem, depending on how good you are at C, but there's one problem you probably didn't see, which is when we run this, it doesn't segfault. It gives us an illegal instruction instead. It's not the same bug, clearly, because it's got a completely different behavior, but our interestingness test didn't catch that. But the other reason why it's not the same bug is that this program is garbage. We are taking, so A is implicitly initialized as an integer because of archaic C rules, and we are taking this uninitialized array of values, and so we're reading uninitialized memory, and we're assigning a value of to A of the wrong type. This program is rife with undefined behavior, and so the compiler is allowed to do whatever it wants to it. So this is a completely sensible thing for it to do, as far as sensible is defined in C land. And so something has gone wrong, and the next 10 minutes or so is going to be unpacking like why this has gone wrong and what this sort of problem means for test case reduction in general. So there are two big categories of problem that you get with interestingness tests, which we call slippage, getting a different bug than you wanted. So the fact that we got an illegal instruction instead of a seg fault, that's slippage. And validity, getting a test case that is allowed to be broken. Like our interesting, in this case, it's that the test case is not free of undefined behavior, and thus the compiler can do whatever it wants, and the property that the executable shouldn't crash is only defined on some subset of C programs. We've moved outside that subset here. These are really the same thing. There are two. A validity problem is essentially slippage to a bug in your interestingness test. Either way, it's that you've got some subset of programs, test cases that you wanted, and you've not been sufficiently precise in defining what those are. We're going to have a brief digression while I'm going to show you some stuff from Hypothesis, because A, I like Hypothesis and I like showing it off, but B, it will give us a nice way of seeing some test cases that aren't just files and how this works in property-based testing land, and also slippage and validity are much easier to see with these examples. So here is a property-based test I often use to demonstrate property-based testing, which is that we're calculating the mean of a list of floating point numbers. And this is one of the, and we're doing it by returning the sum. We're summing the list and we're dividing by the length, which is not how you calculate the mean of a list of floating point numbers, because floating point numbers are also garbage. And this is horribly numerically imprecise, as we'll see shortly. And I never remember how you're actually supposed to do it, because I've read about 30 pages of paper on this, and I still don't understand. But this test will break most implementations I've tried it on. Because what we're doing is we're taking a list of floats. We don't care about nan, we don't care about infinity, because the mean is not well defined for those. And we don't care about empty lists. So that's what this given decorator at the top says. That specifies what kind of inputs we have. And we are saying that the mean is always in the same range of data as the floats we are trying. It's greater than or equal to the minimum, and it's less than or equal to the maximum. It's a perfectly reasonable test. It will fail. Here it fails because adding two finite floats together will give you infinity if they're large enough. And what we've seen here is test case reduction has happened behind the scenes. Hypothesis hasn't told us about it by default, but this is a reduced example. It's only got two elements in the list. It probably started with more. The two numbers are the same and simplified down as far as they go for large floating point numbers. And so far so good. We've generated a counterexample. We've done test case reduction on it. Hypothesis won't give you invalid examples by default. This is one difference from some of the things you saw earlier in John's talk, if you were there, is that in Hypothesis, anything that is given to you by the reducer will also be something that could have been generated. How that works is magic, and I'm not going to go into it because it requires a lot more explanation. But you can still feed it invalid examples if you want to. You can tell it, here, run this example especially. And so, although Hypothesis won't give us an empty list, we can see the validity problem by trying this empty list here. And what happens here is that we try to take the minimum of an empty sequence, and that goes wrong. And so an empty list is an example of an invalid input to this test. The test is not expected to do reasonable things there, and so here's a validity problem. To see slippage, we could have gotten this failure instead. There are at least two logically distinct bugs in this program. One is the overflow to infinity we saw, and this one is a rounding error. Dividing by 3 is not exact with floating point numbers, and what's happened here is we've got these three numbers which are all the same, slightly above 1.5, and we add them together, divide by 3, and rounding happens, and it rounds up rather than down. So we've got, so we exceed the maximum value. And this is a perfectly reasonable test failure. As far as any property we can really define about this test, though, these are interesting in the same ways. They're both an assertion that are failing on the same line. But they are logically distinct bugs, and fixing one bug would not necessarily fix any others. But if we'd started from, sorry, this is really not readable on this projector. If we'd started from this combined example, which was the two examples concatenated together, so it's a 5-element list with our 1.5 blah 3 times and our 8.988 E307 2 times. then when we do reduction on here, we proceed by just cutting bits out of the list. And if we cut the last two elements out, we get the left-hand one, where we've got our rounding bug. If we cut the first three elements out, we get our infinity bug. And so slippage happens because our test is not able to distinguish these, and which bug we end up seeing is essentially completely up to the whims of the reducer. And this is not too much of a problem with property-based testing, because with property-based testing, what happens when you find a bug is that you fix it. And so you can just rerun the test with the same seed or the aid and just see that you've got a new bug. Hypothesis also has a bunch of stuff to mitigate slippage, but that doesn't matter too much. But this is a big problem when reporting bugs upstream, because what happens is you report your reduced bug, they fixed it, and you go, oh, actually, that wasn't the thing I found at all. But you have found multiple bugs, and so there it's not bad. Like, slippage isn't a bad thing, it's just something that will mislead you, particularly because you often slip to easier to find bugs. So in general, how do we develop a good interestingness test? And it's basically just you iterate. You start with a bad interestingness test, you see what happens, you fix it until your final example looks good. And there are smarter things you can do, but it's not really worth it, because this way you can let the test case reducer do all the work. So this is our example beforehand, and I'm not going to show you the other version of the interestingness test because they're even messier. But this is our original one, where we just check that the code compiles and the executable crashes. And so it gave us this illegal instruction. If we do this, but we check specifically for segfault, we end up with this. And this is, again, a garbage program that executes undefined behavior. Here, the undefined behavior is that we've assigned a function pointer to an integer. I think there are other. I think that's the only undefined behavior in this one, but yeah. So all of our examples will have that cheeky infinite loop. It's like I said, I think that is an example of undefined behavior that the compilers don't really exploit, but and so I haven't actually tried to rule it out in any of these. I think discounting those empty infinite loops, I think the function pointer assignment is the only one. And so finally, we refine this by basically adding a whole bunch of undefined behavior checkers. If you look at the C-reduce website, they have some advice on how to do this, but you run it with a whole bunch of compiler warnings and multiple different compilers, and you run with the dynamic clang fsanitize equals undefined checker, and that was the interestingness test I used here. And then you end up with something like this, which is basically okay. It's obviously it's not good code, but we're not expecting it to be good code. We're expecting it to be a minimal reproducing example. And we can then just do a bit of manual tidying, which is usually a pretty common step in like the last bit of your test case reduction, because your test case reducer gets it to the point where it's small and easy enough for you to understand, and it will take you about 5 minutes to tidy it. Here, what I've done is, if you look, this is still undefined because it has some uninitialized variables. It's just that those turned out not to matter, so I manually inserted an equals 0, and I removed a bunch of function predefinition. And so yeah, like I say, manual tidying is usually the final step if you're actually reporting a bug upstream. If you're just using a property-based testing library, it doesn't matter because you now have something small enough that you can figure it out for yourself. But making life easier for the people you're reporting bugs to is usually good citizenship. For interest, this is what shrink-ray would have produced with that test case. It's not nearly as nice, and the reason it's not nearly as nice is because C-reduce understands things like how to inline a C function, which is not something you're ever going to do unless you have something that specifically understands the syntax of C. And this is why specialized test case reducers are always going to be kind of valuable, because you will always find yourself in situations where there is some transformation that depends intimately on the syntax and semantics of the test case. But this is still pretty small. And so this works out mostly okay for a lot of things. And it's certainly better than trying to understand the original 880 whatever kilobyte file. Oop, what happened there? Everything's fine. So where's this useful? Compiler bugs, as we've seen, but compiler bugs are not what most of us spend our time finding. We have, again, this is not readable in this protector, I'm sorry. So here is me being mean to a open source formatting for Python called YAP, which has now been entirely supplanted. But when I was trying it out originally to try and get hypothesis under syntax under a bit more control, I ended up filing, how many did we say? about 47 bugs is the total number. And there it was very much a case of run the formatter, see what fails on the linter, and then run test case reduction to produce lots of tiny bugs. And so all of these were large files from Hypothesis or other projects and turned down to 1 or 2 lines of code when reporting them to YAP. Mostly they didn't fix them, but that was because I think they got bored of maintaining YAP and other better things came along later, or anyway. And oh yes, this is the interestingness test for this, which is, this one is using a modern formatter which didn't exist when I filed those, called Black, but I used an older, simpler one called PyFormat at the time. And so what we're doing here is we are just running a formatter, checking the linter, seeing if there are any errors. If there are, it's uninteresting. If there aren't, we run YAP, the thing we're testing, and we see if there are any errors now. And if there are, that's interesting. And so this gives us a whole pile of bugs and so just running this test on a bunch of files will give us a whole pile of bugs in YAP, and running the test case reducer turns it into lots of nice, tiny, easy to understand examples. And so yeah, we've got language tools of all sorts. Our compilers are mostly pretty robust, but we're using formatters, we're using linters, we're using refactoring tools. So anything that takes a source file as an input language is already a fair game here. But also we've got all these data pipelines. Most programs are just taking some input format and producing some output format. And when those go wrong, they go wrong in production, and you're going to have something passing through it that is some arbitrary user data, and it might be large, it might contain sensitive information, and it's not something you can just copy and paste into your test suite when you're fixing things. And running a test case reducer on that production data and seeing what happened and trying to produce small things for your test suite is another thing where I think essentially everyone who's doing a lot of data, and that's basically everyone these days, should be using something like this in order to improve the quality of their test suites. And as far as I know, almost no one is, because these tools are slightly niche and not enough people are using them. And again, because property-based testing, anything you can test is fair game for test case reduction, because you can write properties, you can generate functions for them, you can use quick check, hypothesis, and your favorite language probably has something like it, although they vary highly in quality. But they're having some understanding of test case reduction and where it goes wrong will often help improve the readability of your test suite quite a lot. So that's roughly what it is, why, and the problems you'll run into using it. I'm just going to talk a little bit about how it works. And this is something that I could give an entire multi-lecture seminar on, so I'm not going to do any of that. I'm just going to give you an idea of what to do when you're a bit stuck and you want something simple that works on your data.
Let's do a tutorial next year, though.
Sure. And basically all it's doing is greedy local search. And what this means is you've got something that says, given this test case, give me 100 smaller variants of it, and I'll try all of those and see what happens. And you do, if you find a smaller one, you move to that and you try again. If you don't, then you say, okay, I'm done, this test case is reduced. There are an awful lot of subtleties to how you pick the variants to try that, depending on where you're doing this, you may or may not have access to. But mostly they don't matter that much. Like if you're doing this on your own time, then all the test case reducer has to do is save you work in debugging. And so spending a lot of time on optimizing all the details isn't worth it. But I will show you how to write one now. So let's write a test case reducer. I do have an apology. I am going to be using imperative programming for this. I know we have a lot of functional programmers in the room. If the sign of a while, if seeing a while loop offends, you may wish to avert your eyes for the remaining slides. So we're writing a test case reducer. This is it's going to be just a very simple command line tool that follows the same interface as creduce. Here's the preamble. We've got a test file, which is the test script we want to execute. We've got an input file, which is our initial test case. We open it, we read it as a string. We're keeping track of the best one we've seen so far. I'm going to try enlarging these so that people can actually read the code, but this may not work. And then we're going to have a test function which takes an arbitrary byte string and, sorry, no, I've used Unicode strings here, an arbitrary Unicode string, and says, is this interesting? Here we're not going to see, now this is light mode imperative programming. We're not going to see how this doesn't work at this scale. This is our main test function. And in particular, this is doing something that I do in basically all of my test case reducers, and as far as I know is idiosyncratic to me, which is that the test function wraps a bunch of local state, and in particular, the test function is responsible for updating our best example so far. So we are creating a temporary directory, we're writing to the file, we're running our test script, we're seeing if it returns 0. If it does, we know it's interesting, and at that point there in the thing, we update our best seen so far. And this is a horrible hack that works brilliantly, because it makes it much, much easier to deal with threading straight through the test case reducer. And so, and it means that we don't have to worry about when we're sort of dividing things up in multiple passes, making sure we update the state everywhere, and it makes a lot of errors impossible. That's true, you heard it here first. Mutability makes a lot of errors impossible. That's literally the only time I will ever say that sentence. And yeah, so now we have our input read as a string, we have our interesting test as a function that takes strings and returns booleans, and it's time to write the actual core of the loop. So this is a very simple line-based test case reducer. The bottom bit is sort of the high-level logic is that we are iterating it to a fixed point. And in our loop, every time we call delete lines, it will, as we saw before, update our current best. And what we do is we iterate backwards through the lines, and the reason we do it backwards is because things in programs tend to depend on things earlier than them. So if you start from the end of the list, you will delete things that use variables before you delete the variables. And so what ends up happening is if you delete going forwards, you delete the last element, then you go to the end, you go back to the beginning, you get to the next line that uses it. And so having this, this is sort of the one trick I would recommend you take away when writing your own test case reducers is try and do deletions in the order of which dependencies tend to occur. But if that didn't make sense, don't worry about it too much because it's not a critical feature of understanding. And so this is what we would call a reduction pass usually. And test case reducers are typically composed of many different reduction passes which do different sorts of transformations. So CReduce has a comment stripping reduction pass, one that inlines functions, and a giant pile of other ones. And if we run this on a source file that comes from the Python standard library, I didn't say this is from the wheel handling, which is part of the packaging stuff. And what we'll see is we'll start deleting lines, and it'll delete a line. It'll try for a bit, it'll delete another line, and so on and so forth. And this has two problems. The first is that it's proceeding very slowly, which, again, if you're writing a production-grade test case reducer, there are ways of avoiding that. I'm not going to talk about them today. Apparently, I'm doing a tutorial next year, so I'll talk about them next year. But the other problem is that what we end up with looks like this. It's not very small. It's a lot smaller than the starting example. And if you look at this, the reason for this is basically that very little of this is actually, I don't know why that one's there. It might be related to what the actual bug is. But very little of this is stuff where you can delete a single line. If you delete this line, then this if statement will fail. If you delete this line, then the body of the if statement will be at the wrong indentation level. Here you'll have an empty body. All of these things, it's not that the line matters, it's that deleting the line breaks the syntactic structure of the Python program, and so the result is uninteresting for essentially validity reasons. And this is really the way where test case reducers will tend to need help, is that there is some syntactic structure that they have to preserve that they don't know how to. Again, if you were in John's talk earlier, the thing that you will often see when people implement test case reducers is you just filter by a validity check. And what happens for these more complex formats is that you can filter for the validity check all you like, but what will happen is that there won't be any valid strings. And so what you need is to give the reducer a way of understanding this a bit more and to know how to actually start to unnest some of the syntax. And I don't fully expect you to read all this code, but this is basically this is basically it. It's a pass we're calling delete indented regions, and what we're doing is we're scanning forward through the lines because I was lazy and decided, and it was harder to write this code backwards. And we get to a line, and we say scan forwards for lines that are either blank or more indented in this line. If that gave us an indented region, we try deleting the entire region all at once. So if you saw those for loops, we can try deleting an entire for loop so we don't run into the problem where the body will get left in a bad state. And we advance the iterator if we don't succeed at deleting. The reason we don't advance the iterator if we do succeed at deleting is because it's put a whole new thing that we can try deleting again in the place if we've deleted a range. So we might delete a for loop and now have that a line starts an if statement or whatever. And so we now change our loop our core loop to just run the two passes. We start by deleting the indented loop regions, then we delete lines. Otherwise, it behaves exactly as beforehand, just with one more pass. And here we start making some good progress. If you look at previously we were seeing like 50 bytes at a time deleted, and we see some of those. But then we see things where it deletes like 2,000 bytes at a time. And this is one of the other nice things about being able to understand the syntactic structure is that you can find these really large and completely irrelevant syntactic regions of your source code that you can just delete all in one blow. And so this ends up, as well as getting to a much smaller example, it actually ends up proceeding much faster. And the final example isn't great, but it's small enough that we can start doing some of the manual tweaking. And I would have done the manual tweaking if I cared about YAP, but I don't, so I didn't. And so this is our final example here. And so that's an example of really like how easy it can be to write a test case reducer, because it's not great. It wasn't great code, and but it also didn't have to do wasn't a lot of it. And similar to how you can iteratively develop an interestingness test, you can also iteratively develop a test case reducer. You can start with something simple, or ideally you start with CReduce or shrink-ray, which I didn't do here because basically both of them do great on this example and produce something much smaller than this already. But you run an existing test case reducer, you get a small example, you say that's not good enough, and then you can start doing your own thing that is a bit more specialized to your format of interest. There are more advanced topics for my apparent tutorial next year. Caching is actually pretty simple in test case reduction, but test case reducers, but it's one of the hard problems, so I had to put it in the advanced topics. But essentially, a test case reducer will often try the same thing over and over again, and so if you can cache the test function, it's really much better too. There are what I call adaptive methods, which is not a thing you'll find in anyone else's approach to test case reduction because they'll tell you about delta debugging, but delta debugging is terrible for reasons I can't get into here. And instead, what all the test case reducers I write is basically, is if you see something that works, try doing lots more of that. So if you manage to delete a line, now try deleting 2, 4, 8, 16 lines in that region, and try and turn long sequences of short reductions into a single large reduction. There's concurrent reduction. Both CReduce and shrink-ray run things in parallel. Shrink-ray is much better at concurrent reduction than CReduce, but CReduce makes up for it by being much better at reduction than shrink-ray. So it kind of, unless you're running on a really big computer, it probably won't win. And finally, there's pass ordering, which is, so we had those delete lines, delete indented regions. What order do we try those in? This one's actually an open research problem. It's really hard to do this in a principled way, but which way you do it has a huge impact on both the performance and the quality of the final result. And we don't really understand why or what makes a difference, and so we basically got a bunch of heuristics and hacks in most of our test case reducers that seem to do an okay job for some reason. So now, I would really like you all to use test case reduction because I think it is a very underappreciated category of tools, and I am personally very excited about it, and I've failed to get too many other people excited about it, so I hope I've succeeded today in at least convincing you that it's interesting. I would like you to try out shrink-ray. I'd particularly like you to try out shrink-ray on weird things that it doesn't work on, and then tell me that it doesn't work on them so that I can figure out why and I can come up with ways of improving its logic. I am going to advocate the use hypothesis. You don't need to care about any of this for hypothesis because the way test case reduction works in hypothesis is completely invisible to the user because it happens at a lower level than you need to care about. But I think hypothesis is good, so if you're writing Python, I think you should be using it, and you can see some of this in action and maybe contribute to the test case reducer in it if you end up finding it's not good enough in some of your cases, which doesn't usually happen these days, but I live in hope of exciting new research there. And yeah, let me know how it all goes. You can contact me either by email or on Twitter. I love hearing about people using this stuff. I don't get to hear enough about it, except sometimes when people get to complain at me about how it's not working in their property-based testing library of choice, and I get to be all smug. But it's, yeah, that's pretty much all I have to say. I want you to use test case reduction. I want you to tell me about it, because I would love to hear more about this kind of thing being used in the wild. Thank you very much.
Questions?
Hey, great talk. Have you experimented with doing the reduction at the abstract syntax tree level? So similar to the way like a auto-fixer on a linter might alter the source code?
So there's an approach called hierarchical delta debugging that does proceed that way, and parses it as a tree and proceeds on that. It's pretty good. The big problem is that you need an abstract syntax tree for the format that you're using, and also that for the most part, it's not quite enough information because you need to know more about the semantics as well as the syntax. And for the things you can do purely on syntax, I've got a bunch of agnostic ways in shrink ray that often work better than syntax tree-based approaches. So there's a whole bunch of research on that, and I personally haven't found it very useful, but that's as much because of the problems I'm interested in. And if you have a format that you particularly care about doing test case reduction on and there isn't a good reason for it, then getting an abstract syntax tree and using hierarchical delta debugging is probably a good choice.
Cool, thank you.
If we are to strike the shrink ray and it doesn't work, should we shrink the test case using the shrink ray?
If it doesn't work, you should definitely give me the shrink ray, the final shrink ray output, because it will be at a fixed point for that. So the final shrink ray output is still a good demo of the bug. You can also try it with creduce and try reducing a file based on the interestingness test that shrink ray fails to reduce it. I don't know how that will work, but if you run into this, I would love to hear about it.
So, at least in this example, we always kept the best possible candidate, right? Mm-hmm. Right?
Yep.
Is it worth trying and keeping a bunch of candidates to avoid getting stuck in the local optimum, or it doesn't happen in this kind of search space?
It absolutely does happen that you can get stuck in a local optimum. creduce will sometimes move to larger variants, like it will try reformatting your file because the reformat might unlock more shrinks. In hypothesis and currently in shrink ray, they're expected to change. We don't do any backtracking. In property-based testing in general and hypothesis in particular, it's because we don't have much of a time budget, and so it's more important to get you an answer fast than it is to get you the best possible answer. But yeah, the question of whether and when you use backtracking is a slightly hard problem, and most of the ones I've designed, I've not found I've needed backtracking, but there are definitely some places where it helps.
Sorry, me again. Has anyone experimented with actually doing this on CI so that if you open up a pull request, it attempts to actually do reduction on bugs being reported and then update the merge request potentially?
I think the problem of automatically creating the interestingness test is too hard.
Okay. I'm just going to do this last one because it might be interesting.
Thank you. So one of the things that is sometimes useful is not backtracking, but to step over a passing test. Mm-hmm. That is, maybe when you've reached your minimal example, then all your attempts to reduce it further lead to passing tests, but maybe stepping from one of them might lead to an even smaller shrinking test. We found that sometimes something that is useful to do at the end of the search. I wonder whether you've tried it in this context.
I mostly haven't tried it for two reasons. One of them is that the design of the hypothesis reducer doesn't make it that easy to try, and the other is that you end up with a quadratic problem, essentially, because if you have n things you're trying to shrink to, and you then try and shrink each of those to another n, then now you've got n squared shrinks. So when I've run into cases where that would help, I've generally tried to figure out new passes I can add that will that will make the transformation that I wanted. In principle, it's a perfectly fine idea, but in practice, I just have found that it's too slow, and I've never really run into a case where I absolutely needed to do it. I just might have required a bit of sitting and thinking real hard in order to figure out why I didn't need to do it.
That's all we have time for. Thank you, David.